Thank you. It's nice to be here. So I want to go back to talking about dust and the formation of planetesimals, and really the linear instability of this. And we heard a couple of nice talks about this yesterday as well. This is going to be based on this resonant drag instability stuff that I did with Phil Hopkins while at Caltech. So I'll kind of go through that and then the more disk-related things. But first, I've had quite a few questions about where the University of Otago actually is. So it's down here in the south of the South Island of New Zealand, probably about as far away as you can actually fly from here. But if anyone's thinking of coming to visit, just I guess the good thing is that Mordor's all the way up here, and the orcs can't cross the water, so it's okay. It's quite safe. Sorry? A little bit, yeah. So yeah, as I said, this talk, I want to be focusing on the growth of small grains into just planetesimal sizes. And it's going to have sort of two different parts for the most part. First will be I'll just focus on the streaming instability, and it's sort of, as we've heard about before, how it relates to inertial waves and disks, and give kind of a simple picture for how it works. And then this new variant that we came up with at the same time called the disk settling instability. And the interesting astrophysical difference about this compared to the streaming instability is that it operates just as fast on small grains, so may have sort of an interesting role to play in the process. And as I said, the method that I'm going to kind of use to analyze this is this resonant drag instability theory. So this applies generally when we have these two coupled systems, and the dust-gas system falls very nicely into this kind of framework. And so it's a convenient way to analyze it. What we do is we just think of all these instabilities as coming about through resonances between different systems, and this gives a nice way to analyze and compute the properties of the instability. So we've already heard a few talks about this, but I wanted to just make sure we're all on the same page and kind of describe the problem to start with and what we actually need to do. So I'm just going to consider like a very small patch of disks so that we can think of it as being homogeneous, and care about the linear stability of this thing. So just if we start with this equilibrium, which is homogeneous on the scales I care about, is it going to stay like that, or do small perturbations grow in time, in which case they'll disrupt the equilibrium and do something different? So the way we approach this, we take our equations of motion, the fluid equations, linearize them, Fourier analyze in space and time, and that leads to something like this. So it looks complicated, but it's not particularly. These delta rho, delta u, etc., they're just the small fluid or density perturbations. K is the wave number of the mode we care about, so both the wavelength and the direction it's propagating in, and this will be important. And then T is the operator describing this fluid system. So that's going to depend on what you care about, the dusty gas system in this case. And that depends on both K and then all of the background quantities, background density, dust density, flows, etc. And what we want to solve for is this eigenvalue, omega, which can have both a real and imaginary part. And of course, if the imaginary part is greater than 0 in my way of organizing the various factors of I, if the imaginary part's greater than 0, perturbations are going to grow exponentially in time, so that means that our equilibrium will be disrupted. So we want to solve this equation to find whether the eigenvalue is greater than 0 and find what that eigenvalue is to see if it's interesting. So in principle, this is a pretty easy problem to solve. This is just a matrix of the size of the fluid system. The difficulties come in because we want to maximize this gamma over all of the K. So over all of the wave numbers for some given choice of equilibrium quantities, right? And this is a three-dimensional vector, so we just have a rather large parameter space to explore. And we don't know a priori which mode is going to give the largest gamma. So, it could be that way, it could be short wavelengths, it could be large wavelengths. So we have to maximize this equation. And although it's simple in principle, computing these eigenvalues can just be a large polynomial, and analytically it can be pretty difficult to tell which are going to give the fastest growing modes and which aren't. So that's kind of where the RDI comes in. So what this theory tells us is that if we have a coupled system, as I said, we're kind of interested in this case where we've got gas coupled to dust and then weak coupling back again. Then if we can find parameters where the frequency of a gas mode, which can be anything really, and then matches the frequency of a dust mode, then what the RDI theory tells us is that this weak coupling from the dust back onto the gas is almost certainly going to give you an instability. So it's almost certainly going to cause gamma greater than 0. And it also tells you that the fastest growing mode is the one where this is the case. So we just look for points in our sort of space of parameters where this is satisfied, and we immediately know that those modes grow the fastest at small metalicities. It also gives a simple formula for gamma, the growth rate, and then sort of physical intuition for the instability, which I'll come back to later. So yeah, just to kind of go through in a wee bit more detail what the system is. The gas is stationary, the dust is moving because of the pressure gradient in a disk. I'll use Z for the metallicity, the dust density of the gas density, and then Ws is this drift velocity. That's going to be set by the pressure gradients. I'll come back to that later. We need this dust frequency if we're going to do this frequency matching process. So the dust frequency we care about is this drift frequency. So if I have a perturbation in my dust, these dots are supposed to show my dust. If I create a density perturbation in the dust, this gets advected by the observer at the speed Ws, the drift velocity. So you have a natural frequency associated with this advection, which is just wave number dotted into that speed. So they just see a time-varying density perturbation. So this is going to be my dust frequency that I match to my gas. So yeah, we just want to take this frequency, match it to the frequency of some gas mode in the system, and then those will be the fastest growing modes, and they're almost certainly unstable. So what this gives us is basically a recipe for finding instabilities in different systems. And we published a bunch of papers on different astrophysical cases, but I'm going to come back to the protoplanetary one later. So basically you start given gas and drag properties, the metallicity, the drift speed, etc. You start, first step is to choose a gas wave that you care about. So whatever you choose here is going to change the instability that you care about. And then you work out the frequency and the eigenmodes of this gas wave. So this could be sound waves, could be MHD waves, could be inertial waves, and I'll come back to that one later, of course, for disks. Step 2, you solve this equation, omega gas equals the dust drift frequency. And this is usually very easy to solve. You just find the K, the wave number where this is satisfied, if it is satisfied. And the RDI theory tells us that these are going to be the fastest growing modes at low metallicity. So these are the only ones we need to care about. We don't need to search through this whole parameter space of Ks to maximize over gamma. And then I said there was a formula that you can use. The formula looks like this. I won't go through its details, but just to say that although it looks kind of complicated, it's actually much easier to work out than you would usually have to from that T matrix. It's much simpler than solving for the full eigenmodes of the T matrix. So that was kind of a very broad overview of the basic theory of the RDI and why this works. If anyone's interested in kind of more detailed maths, how to get that formula, I'd be happy to chat later. But for now, I want to go and talk a bit about the streaming instability. So we're effectively just going to take this recipe that I just talked about and apply it to interesting things in disks. And that's going to be the whole rest of the talk. First streaming instability, then the settling instability. So the first thing, remember, was to choose a wave in the gas. And the obvious one to choose in a disk is the inertial waves, epicycles. And if it's incompressible, then these just have a very simple frequency, kz over k times omega. So this is basically just the angle of the mode in the disk times the orbital speed. And just for reference, this is the coordinate frame I'm using. Thinking about a local patch, z is in the vertical direction. I was radial direction, of course. So then the we need to know the gas drift, which is of course the Nakagawa drift, the NSH drift. So for small grains, this just has this form here, just Keplerian velocity times tau s here is the Stokes number. I didn't really know what thing to use, but just the same as st. So the stopping time times the orbital frequency, and then eta is often used just the ratio of disk height to radius squared. So this is a small number. So the drift velocity has this form for small grains. It's pretty simple. And then remember what we need to do is match the drift frequency here, which comes from that, to this gas frequency, which comes from the epicyclic wave. And then we know that that will give an instability. So if you do this, you find that the resonant wave number you get looks like this. So kz over kx. This is just the arctan or the cotangent of the angle of the mode, basically, and then scales as 1 over the size of the grain, which is what you'd expect. So I think someone showed this yesterday, but this is one of the plots from the original Newton and Goodman paper. I just reproduced it here, showing the growth rates of the streaming instability at some particular parameters as a function of the radial wave number and the vertical wave number. These colors are low growth rates, dark blue is high growth rates. If we take this condition here that I just worked out and put it on this plot, it looks like that, right? So it basically lines up perfectly with the maximum growth rate, which is what we care about. So it's providing a good prediction of the maximum growth rate of the instability. The growth rate itself, if you use that other formula I put down, you end up with something like this. The details don't particularly matter, except that it scales linearly with the Stokes number. And then what this plot here shows is just, it sort of like slices through this plot. It shows as a function of wave number here, so this is going to smaller scales on the right, the growth rate, and then the different colors show different sized grains. So the white crosses here, these are the predictions from this formula here of the fastest growing mode, and you can see that it works really well to predict that fastest growing mode. But I should clarify that the theory only predicts these parts. It only predicts the fastest growing modes. It doesn't predict sort of the shape of this dispersion relation, which changes kind of non-trivially as you change the metallicity and everything else in the system. So I said it also gives a simple physical interpretation for how the streaming instability works. And it does this because we know immediately that it comes along because of this relationship between the inertial wave in the disk and the drifting dust. So we can kind of then back out a physical interpretation of the instability. So this is a diagram showing how this works. So the first thing to point out is that in this diagram, everything's moving to the right with the speed of the dust. Well, actually, k dot the speed of the dust. So both the wave and the dust are drifting to the right. In this frame, the dust is stationary, or the perturbations of the dust are stationary. And there's a pressure perturbation associated with our inertial wave that has a sinusoidal form. We're all familiar with the idea that the dust gets attracted to a pressure maxima. So in this drifting frame, the dust is attracted to the pressure maxima, which will, from the back reaction of the dust on the gas, exert a force which increases those pressure maxima. Pressure maxima gets bigger, has a stronger force on the dust, pulls it into the pressure maxima, increases the pressure maxima. You can see how this would run away as an instability, right? And Martin pointed this out the other day, that this requires 2D perturbations. The reason it requires 2D perturbations, which I guess is different from previous models, is that in drawing this picture in the first place, we've implicitly gone into this frame where everything is moving at the same speed. And because the inertial wave has its dispersion relation is just the vertical wave number over the total wave number. If you have a wave that's got no vertical wave number, then it has zero frequency, it's not a wave, and so this picture no longer works. So sort of implicitly, by even drawing this picture, we have to be in a 2D situation, which is why the streaming instability only works in 2D. Just to quickly say, as a kind of aside, in the appendix of our paper, we talk about how there's actually a different instability that comes along at high metallicity. So there's two different modes. The RDI one still stays unstable, but then there's this other non-resonant instability that comes along. And it has a growth rate that basically is the square root of the metallicity minus 1. And so this can get very fast, much faster than the local orbital time, but it does move to very small scales. So this is just showing, again, growth rate as a function of wave number for different size grains. And you can see it can grow very fast, but only on very small scales. But this is presumably some relation to why it works so much better at clumping grains at high metallicity. Okay, so that now brings me to this new variant, the disk settling instability, which is sort of the cousin of the streaming instability in a way. With the big difference that it has large growth rates for small grains, so there's no dependence on the grain size anymore of the growth rate. So the motivation for kind of looking into this, streaming instability is certainly a promising mechanism for forming planetesimals, but there are some challenges that we've heard about in this meeting. Doesn't work so well for small grains, and it seems to require higher dust density than would be predicted from minimum mass solar nebula or something. And that probably gets a lot worse with some of the stuff we heard in Martin's talk yesterday. If you have a spectrum of grains, these problems likely get a lot worse, but we can ignore that for the moment, except to say that I guess it's not obvious that the streaming instability is an easy mechanism to form planetesimals. So this is just showing this, I think we saw it yesterday too. The red regions are where streaming instability doesn't seem to work very well, green where it does, as a function of grain size and metallicity. So somewhat above solar, it sort of drops down to zero. So kind of motivated to ask, are there other possible mechanisms that could help in the process of creating planetesimals? So the reason the RDI stuff is helpful for this is that we can just take that recipe again and apply it to other things in disks. So the streaming instability came around from a kind of specific situation. What do we get if we apply to other waves and other dust motions? So if you do this, you get all sorts of stuff. And most of them are not very interesting, either very small scales or very low growth rates. But there are a couple that seem to be quite interesting that we've called this disk settling instability. It's sort of hard to know what to name these things because everybody's taken most of the names, but if anyone has any better idea, we could change it. So the idea is the same as before. You just start from an inertial wave, same frequency as before. You can add in compressibility if you want. Then all we change is change this drift speed into the settling drift instead. So transient phase as the dust drifts downwards has this sort of drift velocity. There's also a radial component that I've only, and the only real big difference compared to the other case is that there's this factor eta to the half here, and it can go in either direction, of course, whether or not you're above or below the disk. So eta to the minus a half is big, of course, but then we just do the same process as before. This thing equals that thing. Work out where in K that occurs, and if you do that, you end up with this. Not really supposed to get much from that, but the growth rate ends up going like this. So omega metallicity to the half, Kx, but you see there's no factor of the Stokes number in this equation now. So it's effectively scales as Stokes number to the -1 times the growth rate of the streaming instability. So for small grains, this is much faster. This is sort of the main point. So to put this in a different, sort of more pictorial way, if we have our grains streaming along the midplane, this is the streaming instability, leads to growth rates that look like this, different grain sizes, decreases with decreasing Stokes number. and also goes to smaller scales, of course. If instead we study the situation where grains are streaming downwards, as well as radially, then the growth rate plot looks like this. So I've effectively used the same parameters, but with including vertical streaming now instead. And I guess the key difference is that whereas these growth rates go down linearly with Stokes number, these ones stay pretty constant. In addition to that, this one has larger scales. So you can see this one's, if we compare Stokes number 0.1, it's sort of 80 or something, whereas this one's kind of 8. And that's just because of that, the drift itself is much faster with the settling drift. So to go into this in a wee bit more detail in the last few minutes, sort of how this mode behaves, what it looks like. So this was my plot. If I now take these very small grains, 10 to minus 3 Stokes number, solar metallicity, and then plot how this thing varies with mode angle. So again, I'm plotting growth rate versus wave number, but these different curves show different mode angles. So like here, this is a nearly vertical mode on the left. So it's large scales, but small growth rates. As we move to more and more radial modes like that, the growth rate increases until you actually reach this point here. There's this critical angle where the growth rate goes to infinity. And if you compare it to the disk frequency, the growth rate can actually, it can overtake the disk frequency at this particular angle. We call this thing the double resonant mode. And yeah, it might be interesting. It is on small scales, but it can grow very fast. So just to say, we've checked this mode against compressibility, vertical stratification, and other things, and it seems to be quite robust. So this leads us to suggest this kind of astrophysical scenario where the settling instability could act as a sort of primer for the streaming instability. So the first point is that if the Stokes number is less than 1, growth time is much less than the settling time. So any small grains, this instability has a long time to grow as they settle downwards in the disk. So as they settle down, you would expect the grains to clump. And remember, it's these nearly radial modes that are growing the fastest. So they're clumping mainly in the radial direction, like that. If we go back to our challenges, it wasn't very effective for small grains and seems to require too high dust density. So the ways this might be able to help with that, first, I mean, you get clumping of small grains. In fact, should be preferential clumping of small grains because they have more time to settle, aside from the effects of turbulence, everything. So this would be a laminar process rather than turbulence, so you don't necessarily have these same limits about shattering and everything, because grains can be brought together quite slowly. And then the second thing, so you would kind of naturally end up with radially clumped dust, because as it falls down, it clumps radially due to this instability. So you could end up with higher local metallicity regions in the midplane, and you potentially only need a relatively small factor to make the streaming instability work a bit better. Of course, how this relates to the spectrum of grain sizes and this kind of thing is, we have no idea, but it's at least an idea. So I should say this is purely linear instability at the moment, and it definitely requires simulations to explore things a bit better. Unfortunately, you have to resolve the full scale height so that you can get, or at least a good fraction of it, so you can get a lot of settling downwards. You also have to resolve pretty small scales because you care about the small grains. So they're challenging, but they are doable. And if anyone's interested, there are some estimates of how different simulations how close different simulations got to this regime in our paper. So that's about all I wanted to say. Just a few quick conclusions before I get really tangled. So the first point was that this resonant drag instability method gives us a pretty easy way to find instabilities of dusty gas systems, and you can do it with sound waves or MHD waves, and these have interesting applications in lots of different arenas. Applied to disks, we kind of rediscovered, well, not rediscovered, but found the streaming instability fit inside this framework. And this led to simple expressions for its growth rate, how it behaves, and understanding of its kind of a sort of toy picture for how it works, at least at low metallicity. And then this disk settling instability, very similar instability, same type of structure and everything. But its big difference is that it grows fast for small grains as the grains settle, which might be interesting, but we still need simulations to explore this properly. So thanks.
Thank you very much, Jonathan. Oh, many questions. Let's start.
There we go. So my understanding and experience with pressure bumps and drifting into pressure bumps is that the momentum exchange then destroys those pressure traps. Right. What's the difference here that makes them actually reinforced?
So these are, so in this kind of very toy picture, I should say, this thing, these aren't necessarily pressure traps. These would be high dust density regions.
Well, I guess I was referring to the cartoon of the streaming instability, where you had those
right, hills, okay, sorry. So the big difference is that the wave is moving at the same speed. So whereas in the standard pressure trap scenario, you have a static one and the dust kind of stops in it and then builds up to very high densities as well. This is, first it's a picture at metallicity less than 1. Mm-hmm. And second, everything's moving along at the same speed. So it's that kind of concurrent drift which allows it to build upon itself.
Yeah.
Okay, so let's do these three over here, and then we'll move across the room. So Martin, and then...
The square root dependence of the growth rate with the metallicity, that's quite generic for any resonant drag instability. For low metallicities. For low metallicities.
Almost. There is a different regime that comes around in certain cases, but generally, yeah.
But then, isn't this a case also for the settling instability for low metallicities? Wouldn't you get a growth rate that goes to square root of a
yes, you do.
Because the point is that I think this could lead to the same issues that I discussed yesterday. You're pointing out here fairly enough that the Stokes number doesn't enter into the expression for the growth rate, but if the square root of the dust to gas mass ratio enters, I think that the reason we keep seeing decays when each individual dust species receives less mass because there's a spectrum, then the growth rate will decay.
Quite possibly. I don't know. I think we need to explore this. So there are some differences which might change things. I'm not saying they will or they won't, but there are differences between the two, and it seems like your result relies quite a bit on how wide the resonances are and different as you decrease things to 0 and how this scales, and maybe that's related to different regimes. So quite possibly, I don't want to say yes or no. I think we probably need to look at it.
All right. Thanks.
I have a very large box simulations covering plus minus 0.8 gate scale height with 160 cells per gate scale height.
Yeah.
If that suits your need, I'm happy to give it to you. It includes sedimentation.
So this is beyond your paper from 2017 and
2014.
So I did look through these simulations, and I think your simulations were the closest ones in the literature to resolving everything. But they were sort of a factor of few off. Yeah, this is, I mean, yeah. So this is what I mean by it is feasible, but
But since you are only interested in the linear phase, it's very cheap, so I can run again and
great,
do it for you.
We should chat. I've been meaning to talk.
So this is on the I guess in the same line of the last question, because you were showing that for small grains, the growth rate will keep increasing with the wave number. So if I understand correctly, if we want to simulate this instability, we will never reach the necessary resolution to correlate capture the maximum growth rate. And if you want to reproduce an instability, you always should be worried to resolve the maximum growth rate scales, right?
I think we can. So you have to be in between. You don't want to be too low tau because then grains settle very fast and you don't have any time to see the instability. If you go to too large tau, then it has ages to grow, but you run into the problem you said. But in between, say a hundredth or a thousandth, I think it is possible if you look at this particular regime. So kind of, millimeter to centimeter size grains, it should work. Yeah.
So which size is the one that you were showing that grows, keeps growing with the growth rate, with the wave number?
Oh,
there was a plot before?
Was this the high Z instability? It's not going back. This one?
No, the one that you have the growth rate going to
infinite.
infinite.
Oh, right. Yeah. So that was at 10 to minus 3. Stokes number 10 to minus 3, and you can probably just resolve this mode. Yeah.
But the growth rate keeps.
Right. You'll need. Right? I mean, yes. I see. So numerically, right, you're going to run into the grid scale at some point. Whatever you resolve, the fastest growing modes are smaller than that.
Yeah.
Okay, I think maybe we should continue this in the break, and so we get a little bit. So Vlad, and then Till, and then.
Hello. About the interpretation, right? That Jake also asked. That you have a bump, right? And then that bump will get more dust, and then you drag gas into it, right? And then because the pressure goes up, then you get more dust. Mm-hmm. That was the original picture we had, right? To try to explain that, but I have a problem with that there is nothing 2D about it. Right?
Nothing 2D. No, there
exactly.
is. So that's actually
it's all 1D. Yeah.
No, so I agree that in 1D this is the original picture, and the 2D thing is really probably the only new thing in this. So the reason it has to be 2D is that you assume that everything is moving at the same speed. This is only possible for a 2D wave because because the frequency of an epicycle goes to 0 and for purely radial waves. So you have to have a wave that has a vertical wave number for this picture to even be able to draw this picture in the first place. Once that's the case, you can draw this picture, and then this is kind of a basic description of the mechanism.
Sorry, wait, Till?
So I was wondering how...
yeah, exactly.
how robust is this settling instability against diffusion?
I mean, it happens on relatively small scales. If you estimate how robust it should be, you end up with pretty similar results to the streaming instability, maybe slightly better just because it's on slightly larger scales. So a factor kind of 8 to the half better. It's pretty hard to tell without doing actual simulations. I mean, something like it could also depend on the anisotropy of the turbulence, like whether it's vertical streaming instability or some other source of turbulence. I don't think we can really know that unless So we did have some estimates. At alpha 10 to minus 4, it should be okay for Stokes number 10 to minus 3 grains, but it's getting a bit iffy. For bigger grains, it should be sort of okay. So there might be some sort of threshold. Once you get big enough grains, you can then start this process. Yeah.
Okay, very quick last question, Jeremy.
Yeah, that's a good idea. So if anybody is thinking of this, you do need to keep the rotation. That's the only key part. But yes, if you do that, it should still work. So that's an interesting idea. Yeah, I think you could actually.
Okay, with that, let's please thank Jonathan again.